Hello students, welcome back. We just completed section 1. Now let's go to section 2, orbits and cycles. Section 2 will require some change of viewpoints, especially early on. So far, we had been considering groups and their elements as objects. For example, sets of numbers and numbers. And then we used to apply something, such as functions, to those objects. But then again, here in lesson 5, we are studying groups of maps. So in this case, each element of a group is a map, and that's being applied to some other objects. And then how are those objects being moved around by those maps? You see, you have to take different viewpoint. And one such example is this one here, orbit. Let's begin. Let capital A be a non-empty set, and let sigma be a permutation on A. That is, sigma is a bijection. It's a one-to-one onto map. Then, the orbit of small a under sigma is defined as a set of all sigma to the nth power of a's, like this. The orbit of a under sigma. The orbit consists of the forward and backward orbits. Forward orbit goes like this. A goes to sigma of A, sigma squared of A, sigma cubed of A, and so on and so forth. As we apply sigma over and over again. Now, this is called a backward orbit. We are applying sigma inverse over and over again. A to sigma inverse of A, and then sigma to the negative second power, negative third power, and so on and so forth. Put these two together, we get an orbit. Now, I use the term permutation here. So, A is a finite set. Yes, you may be able to consider permutation in infinite sets, but this is abstract algebra 1, so we don't do that here. Maybe in abstract algebra 2, maybe, but here, whenever I say a permutation, it's a bijection on a finite set. So this is a subset of A. You see, everything is within A, so this is a subset of A. So this is a finite set too. So whenever you have a finite set, one natural question is, what's the cardinality? The number of elements there. Or in other words, how long does it go? You see, this will not go on forever. At some points, this will have to stop, and you're going to get a duplicate elements here because the orbit is finite. And that concept is called the length of orbits, and that's the next topic. Let's consider the cardinality of this finite set, which we call the length of orbit, and intuitively, this one really looks like a length. It turns out the length of orbit works very similar to a certain formula that you saw before. Which is it? Haven't you seen something very similar in lesson 4 when you studied cyclic groups, finite cyclic groups, the order formula for finite cyclic groups? Remember that? If you take away A and rewrite everything like this, let's see. Let me copy and paste so that I don't screw up this part. And then let's see, this one here, I can rewrite as sigma to the 0 power here. Because 0 power is identity map. And then let's consider this. Throw away this A. Throw away that A. Throw away all those applications to A. And look at only those elements of group or this map as an object. Then what do you get? You get the order formula of finite cyclic group. And then this thing here, again, I can rewrite it as the sort of A, but throw away A. and then throw away A, first power, and throw away A. You see, throw away A, and then this one is just, now you can rewrite like this, and then the order of that is M. Well, these are exactly the same formulas that we went through in lesson 4. Remember those? So if you discard A and look at these those maps, sigmas, as objects of the, and then consider those groups. Consider sigma as objects, and then do not consider it as a map, then you get the order formula for finite cyclic groups. Now, if you consider those as maps applied to A, then you get orbit formula, length of the orbit formula. Similar thing, but viewed in different viewpoint. Am I making sense here? See the similarity here, or identical nature. This versus that, and this versus that. They're the same. Of course, the difference is applied to A, so that'll create a bit of a difference. But then again, if you do not dwell too much upon that, then you'll see the similarity or some identical nature of those. And that'll help you getting the proofs of those. We end up using exactly the same argument as in section 4. Excuse me, in lesson 4. I think section 3 of lesson 4, the equivalence of the first and second minimum using taking a negative of the right hand side and flipping over. Remember this? And then proving this formula here, this identity here. One inclusion is obvious because of the definition, yes. And then the other inclusion is the problem, and we use the division algorithm. And then sigma to the R plus Qm, and the Qm, that is repeated application of sigma to the m power, which is just coming back to A, and that is being repeated Q times, so just A. In the end, same idea, division algorithm. Exactly the same as what we did in lesson 4. And finally, the proof that these are all distinct. Again, the very same idea. The only thing that we did differently is apply to A. That's about it. I hope you guys see all those. I mean, you ladies and gentlemen see all those. So change of viewpoint. That may be a bit hard, but once you do that, now it's easy because we are recycling exactly the same technique. You see, flipping over and getting the equivalence, and then the division algorithm. Now, we can go all out and observe that they're not just related, but they're actually the same. And we can do it like this. In the orbit, we just define a binary operation induced from those given by the composition map like this. And then we can prove that this orbit is actually a group, and not just a group, but it's a cyclic group. Once you prove that, then everything that we did for finite cyclic groups come right forward. Either way, they'll work out. Either way, you can see the similarity between one and the other, basically the change of viewpoint. Okay, so much for 2.1 and 2.2. Now, 2.3 is also a change of viewpoint, but not directly related to lesson 4. What we want is to decompose the original starting set with some disjoint union of different orbits. But then again, it follows immediately from equivalence relations and equivalence partitions. It's not what we did in lesson 4, but that's something we did in lesson 1, if you remember. Suppose that we prove that this is actually an equivalence relation. If you do that, then we can consider equivalent classes, and those are given by sigma to the nth power orbit. So basically we are going to get the orbit. The equivalent classes are orbits. So being equivalent classes, the orbits are either disjoint or identical, and then unioning them all, we're going to cover entire A, so you're going to get a decomposition like this. So we get equivalent partition and decomposition. But then again, of course, if you prove that this is an equivalence relation, all these follow. Are they really equivalence relation? Or excuse me, is this really an equivalence relation? Well, we have to do these three: reflexivity, symmetry, and transitivity. Reflexive, yes it is. All I have to do is consider sigma to the 0 power. Symmetric, yes indeed. All I have to do is to convert nth power into negative nth power. How about the transitivity? That needs a bit of work, so maybe you can stop the playback and then try it on your own. Do you get it? It follows from the algebraic operation. A is related to B and B is related to C, then B is mth power and C is nth power. So if you compose, then you get m plus n power. So m plus n is also integer 2, so A is related to C as well. You get the transitivity 2, and thus this is an equivalent relation, and therefore we have equivalence classes and equivalence partition, and those equivalence classes happen to be the orbit, and the equivalence partitions turns out to be the decomposition by disjoint orbits. Now, the other two are about cycles, and that's something we'll have to discuss in a separate video. As for 2.1, 2.2, and 2.3, remember, change of viewpoint. If you change the viewpoint a little bit, then these things become easy. 2.1 and 2.2 are related to taking the viewpoint of finite cyclic groups. And 2.3 are related to utilizing the equivalence relation. Okay, so much for the first half of section 2. We'll do the second half in a second video.